go to the heteronuclear diatomic molecules. What do you understand about heteronuclear diatomic molecules? Okay, so we have molecules, okay, that contain more than two different atoms, okay. But this one, okay, for this topic, we will discuss about hydrofluoric acid or hydrogen fluoride. Second one, we will discuss about NO, and then we will discuss about CO, okay, carbonyl, alright. So, how to draw, okay, this kind of molecular orbital diagram for heteronuclear diatomic molecules, okay. So, first thing is, okay, as usual, you need to draw the energy. Okay, you need to draw the energy first. Right? Okay. Second step, okay, you need to have the atomic orbital of hydrogen, and then you need to have the atomic orbital of fluorine. Okay? Alright. And then here at the center, you need to have the molecular orbital for the hydrogen fluoride. Okay. So, as usual, you need to write down the electron configuration for hydrogen and also fluorine. Okay, so hydrogen you have here is 1. Okay, while for the fluorine here, you need to have, okay, let's check the proton number for hydrogen, 9. Okay, so 9. Alright, so write down first the electron configuration for hydrogen, 1s1, while for the fluorine is 1s2, 2s2, 2p, 2p5. Okay, alright. Okay, so 1s2, 2s2, sorry, 1s2, 2s2, 2p5. Okay, so, okay, you need to determine, okay, other than that, okay, alright, you need to determine which one is more electropositive and which one is more electronegative. Okay, alright, if you compare between the hydrogen and fluorine, hydrogen is more electropositive, so it will have higher energy. Okay. Right, compared to the fluorine here, okay, so we have the 5, you need to show the 2p5 here, alright, so fluorine is more electronegative, so it will have less energy, okay, so 2p5, okay, so this is 1s and this is the 2p, okay, alright. Okay, other than that, you need to know that hydrogen, the shape of hydrogen is a circle one, okay, while for the fluorine is actually from P group, okay, it has loop, okay, so it's actually interaction or overlapping between N to N here, okay, N to N here, alright, okay, so what happened here, okay, you need to have one here, and here, alright, so this is the 1s, how many electrons do we have? 1, while for the fluorine here, we have 5, right, so 1, 2, 3, 4, 5, okay, alright, so as you know, alright, the orbital diagram or the number of orbital for this one and this one must equal to the center. Okay, so we already have 1 here and 1 here, and we need to fill up another 2, right? So you need to fill up here. Why? Okay, because this is where the orbital that actually do not involve in the overlapping. Okay. Alright, so how many electrons do we have? Okay, 1, 2, 3, 4, 5, 6. Okay, so fill up. Right, 1 here, 2, okay, and then 3, 4, 5, 6. And this one will be the sigma. Okay, while this one will become sigma star. Okay, alright. So then you need to, okay, you need to show the interaction between hydrogen and fluorine. Okay, hydrogen and fluorine. Well, for this one, it's actually a straight line, okay, where these two orbitals do not involve in the interaction. So this is the molecular orbital for the hydrogen fluoride. Okay. Okay. Next, okay, so here this is how you need to draw the molecular orbital diagram for hydrogen fluoride. Okay. So as I explained before this, okay, we have difference in energy between the hydrogen and fluorine because hydrogen is more electropositive than fluorine. Okay, so the 1s will have higher energy here compared to the 2p. Okay, and then this is where you have 2px and 2py. Okay, where you these two orbitals, okay, do not involve in the overlapping. Okay, right. Second one, how to draw the molecular orbital for NO. Okay, right. As usual, you need to list down, okay, the N and also O. Okay, what is the proton number for N? 7. Okay, while for the oxygen here, so for the nitrogen is 1s2, 2s2 and 2p3. Okay, for the oxygen is 1s2, 2s2 and 2p4. Alright, so this is where you have the overlapping between P group. Okay, so you need to show the valence electron of these two, nitrogen and also oxygen. Okay, first thing is you need to draw as usual the energy. Okay, the energy level. Okay, so let's start with the 2s energy. Okay, alright, 2s level, sorry. So here is the nitrogen and this one is for oxygen. Okay, nitrogen and also oxygen. Right, then we have here 2s. Okay, nitrogen is more electropositive than oxygen, so it will have a little bit higher energy compared to the oxygen. Okay, so this is the NO. Okay, then alright, you need to have the sigma here. So this is the 2s. This is the 2s, while this is the sigma 2s. Okay, this is sigma star 2s. Okay, how many electrons do we have here? We have 2, maximum number of electron. Okay, alright. So what happened here? Okay, let's change the pen color, green. Okay, 2 plus 2, you will have 4, right? So you need to fill up the sigma 2s, 2, and also sigma star 2s. So 4. Alright. And then next level. Okay, next level will be the 2p. Okay, will be the 2p. Alright, okay. So remember that nitrogen is more electropositive than oxygen, so it will have higher energy compared to the oxygen. So the 2p here, and then this is the 2p for oxygen. So this is the 2p. This is also for the 2p. Okay, and then okay, all the heteronuclear diatomic molecules, they follow what we call with sp mixing. Okay, with sp mixing. So you need to start with the pi. Okay, and then followed by the sigma. Okay, 1 to 1 2. Okay, then followed by pi star and also sigma star. Alright, so this is the sigma star to p. Okay, this is the pi star to p. Then we have the sigma to p and pi to p. Okay, alright. So how many electron do we have here for nitrogen? 3, 1, 2, 3. And this one we have 4, 1, 2, 3, and also 4. Alright, then let's change the pen color. Alright, so 3 plus 4 you will have 7. So fill up. Okay, here 1, 2, 3, 4, 5, 6, and also 7. Alright, so okay, this is the molecular orbital for NO. So where is actually the LUMO and also HOMO for these molecules? Alright, so where is actually the LUMO and HOMO? Alright, the LUMO from here, lowest unoccupied molecular orbital, is where you have 0 electron. Okay, zero electron. So here, okay, where is your 0 electron? Sigma star 2p. This is your LUMO. Okay, while where is your highest occupied molecular orbital? HOMO. This is your HOMO. Okay, alright. Okay, so what is the dimagnetism? Dimagnetism. Okay, susah juga nak tulis ni. Dimagnetism. Okay, what is the dimagnetism for this NO? Para or diamagnetic? The answer is paramagnetic. 1 unpaired electron. Okay. Okay, so this is the molecular orbital diagram for NO. Okay, so from the molecular orbital diagram, you can determine the possible Lewis structure. Okay, the correct Lewis structure from here. So as you can see, okay, we have the possible Lewis structure here. Okay, if you compare this one and this one, this is better. Why? Because for the formal charge, we need to determine as we need to find the formal charge, the lowest the possible. Okay, alright. So this is the answer. As you can see, we have 1 lone pair here. 1 unpaired electron. So the most stable one, if you have these 2 Lewis structure. Okay, if you have 1 lone pair at oxygen, you will get positive 1, right? But if you have 1 1 unpaired electron at the nitrogen, you will get 0 here. So the answer is this one. Okay, this Lewis structure. Right. So next we go to the molecular orbital diagram for CO, carbonyl. As usual, you need to follow this sequence, okay, or this arrangement of the molecular orbital diagram, okay, with sp mixing. Start with the pi to p, sigma to p, pi star to p, and sigma star to p. Alright. So as you can see from the molecular orbital here, okay, this CO is actually a diamagnetic compound because we have paired electron. Okay, and the possible Lewis structure is like this. Okay, 1 lone pair at the carbon and 1 lone pair at the oxygen here. And where is actually the LUMO and also HOMO? LUMO and also HOMO. Okay, so this one will be the LUMO, lowest unoccupied molecular orbital with 0 electron, while the HOMO is the highest occupied molecular orbital. The HOMO is here, at here, okay. So, LUMO is the pi star 2p, okay, pi star 2p, while for the HOMO is where you can find at the sigma 2p, okay. Alright, so as usual, you need to show from the 2s and then followed by the 2p. And you need to show the difference between the energy between carbon and also oxygen. Okay, alright. Carbon is more electropositive than the oxygen. So, alright. Next is the molecular orbital in benzene. Okay, let's draw the structure of the benzene. Okay. This is the structure of the benzene. As you can see from here, we have 1, 2, 3, 4, 5, 6 sigma bond and 3 pi bond. Okay, 6 sigma bond and 3 pi bond. Okay, so from here you will have, okay, as you can see, okay, the shape or the hybridization for each carbon here is sp2 orbitals. Okay, this is from the top, okay, while from the side view here you can see the pi. Okay, so this is 1 pi. We have 3, right? Okay, and then this is the second pi and this is the third pi. Okay, alright. Okay, while for the sigma, we have 6 here. Okay, this is 1, 2, 3, 4, 5, and also 6 sigma. Okay, alright. Okay guys, in this, each carbon here, as I said before, we have sp2 hybridization. Okay, sp2 hybridization. Alright, 6 sigma bond between the carbon and carbon and 6 sigma bond between the hydrogen. Okay, 6 plus 6 here. Okay, alright. And another one is, okay, let's say we have eraser here. Okay, then we draw another one in yellow. Okay, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, okay, plus 6 sigma from the carbon and also hydrogen. Okay, and then as you can see here, we have electron density of the pi bond delocalized over the entire molecules. While why delocalized? Because we have the pi. Okay, we have 3 pi bond. And then we have unhybridized 2p orbitals. Okay, this is where you can find the pi. Okay, in each carbon atom overlap and form pi bond. And because of this, of atom distribution on the p electron, this is the p electron. Okay, so it makes benzene is one of the molecules that unusually stable. Okay, because of the sigma and also the pi bond. Okay, delocalized pi orbitals. Okay, second one. Okay, here we have the molecular orbital in ozone or O3. Okay, let me change the color here. Okay, alright. So we have 2 possible Lewis structure for the ozone. Okay, whether for the first one or second one. Okay, both are correct. Okay, alright. Then so here we have pi bond form between sp orbital of each oxygen in O3. Okay, alright. Because we have this is sigma, this is sigma, and this is a pi bond. Okay, and then the pi electron delocalized throughout the entire molecules. It can be here, or it can be here, or it can be here or here. Alright, so delocalized, okay, bergerak. And then the bond length between the O and O is not single bond or double bond, but in between single and double bond. So from this one, you need to determine the bond order. Okay, the BO, bond order. Alright, okay. So this is where you have the sigma. Okay, this is where you have the pi bond. Okay, it can be here or here. Right? Okay. So next is the example. Okay, this is example for nitrogen 2 plus ion that can be prepared by bombarding the nitrogen 2 molecule with fast moving electrons. Okay, so when you see this kind of question, okay, let's say it require you to write down the electron configuration. The answer is not like this: 1s2, 2s2, 2p, and blah 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 blah. Okay, the answer must start with the sigma, and then followed by pi, and then pi star, and sigma star, or vice versa. The bond order, you need to remember what is the formula for the bond order and the magnetic properties, whether it is actually magnetic or diamagnetic. Okay, alright. Okay, so these are the answer. Okay, alright. So here, I need you to do this exercise, guys. Okay, I need you to do this exercise number 1, number 2, and also number 3. And we will discuss this exercise during our class, okay, in Microsoft Teams. Alright, every Monday. Okay, so please do these 3 exercise. So alright, okay, first one, you need to sketch a name. Second one, you need to explain which species has the longest bond, and last but not least, you need to draw. You need to be able to draw the molecular orbital for cyanide. Okay, right. So that's all for today. So I'll see you guys on the next class. Okay, on the next video. Alright. That's the end of our lesson for this for today. Okay. So I will put a new video on the next chapter. New video on the next chapter. Okay. So that's all for today. I will see you again. Bye.